Okay, let's take up few examples of Fundament diagrams. So first I will look at two-point function. Okay, and remember that I am only looking at the numerator in the master formula. Okay, we will talk about denominators later. So two-point function, so I am looking at okay. So let's look at order 1 term, meaning order lambda to the 0 term. So you have two external points x1 and x2, and there is no vertex because you are at order lambda to the 0. Okay. And there is one possibility that you connect these two. Okay, and this is just the Feynman propagator. Now let's go to order lambda. So again I have my two external points x1 and x2, and at order lambda you have one vertex. Okay, let's call it z. So now I can connect this, and I could connect it like this, and then I am left with this possibility. So this is one possible Feynman diagram. There is another possibility that we do the following. So instead of connecting x1 to a vertex and x2 to a vertex, I connect x1 and x2. Okay. And then these lines coming out of this vertex, I connect them among themselves. So that's another possibility. Okay, so this one will have delta d of or df z minus z, and this one also df z minus z. Okay, so this is these are some examples. Let's look at what kind of diagrams you get at order lambda square. So as before, always start with putting x1 and x2. I am not drawing this one tick out of it because you know that you can only just take out one line out of these external points. So I am not going to put that tick every time. So at order lambda square you have two vertices z1 and z2. Okay, and there are many diagrams that you can draw with these two external points and these two internal vertices. Let me draw a few of them. So of course you can, let me write z1 here and z2 here. Of course you can draw a line between x1 and x2, so that's a Feynman propagator df x1 minus x2. And then there are many ways in which you can contract these, and one possibility is that you contract this with this one like this, and connect these two. So this is one possible Feynman diagram at order lambda square. Okay, there are more, some of them I will draw, so you can easily convince yourself that this is another possibility. Okay, so you have one vertex here, one vertex here. So there is 1, 2, 3, 4. 4 lines coming out of this vertex, and same here 1, 2, 3, 4. Okay, so this is another order lambda square diagram. Maybe one more I will draw. So you can have this, you connect the external points x1 and x2, and then the 4 small lines that come out of each vertex, all of them can connect to the other vertex. So you can have like this. So let's say this is vertex z1, z2, and there are 4 lines coming out, and I contract them like this. Okay. So at this vertex you have 1, 2, 3, 4, and here 1, 2, 3, 4, and you have connected. So this is another possible diagram, and you can draw other diagrams as well. So this was an example for 2-point function let's look at some of the look at two diagrams and look at their combinatoric factors, right. So, I want to look at combinatoric factors. So, let us look at this diagram. I think I drew it. Yeah, this is this one. Okay. So, in how many ways I can draw this diagram and get the same expression? So, all the ways in which this diagram can be drawn, that will be the combinatoric factor, and let us count. So, start with x1, x2, and then you have this vertex. So, x1 could go to any of these 4 lines. X1 cannot go to x2 because I am looking at this topology, right, where x1 is connected to the vertex. So, x1 could go to any of the 4. So, it goes, let us say, to this one. So, I have 4 possibilities here. Then x2 could go to any of the 3, right, because they all are equivalent. So, x2 could go to any of the 3. So, there are 3 possibilities. Then this guy can connect only here. So, there is only one possibility. Okay. So, you have 12 such diagrams, and they all contribute same, they all have the same expression. Okay. So, the combinatoric factor is 12 for this case. Let us look at another example. This one. I want to look at this topology. Okay, this one. So, there is a vertex here. Let me draw it nicely. Okay. So, we want to again know the factor corresponding to this one, and that is easy. Let us see. So, this one can go only to this one because these are connected, right. So, x1, x2, there is only one possibility. Now, this guy, let us start with here. This guy could go to any of the 3, remaining 3. So, let us say it goes here. So, you have 3 possibilities. Then this one has only one possibility. So, the factor is 3. Okay, let me give you a slightly more complicated example. Now, I want to look at 4-point function. So, you have x1, x2. Maybe I should first draw the diagram. So, I am looking at this one. So, there is a vertex here, there is a vertex here. Let us call it Z1, let us call this one Z2. So, this is the diagram for which I want to know the combinatoric factor. So, let us see. So, I start by again putting x1, x2, x3 and x4. So, these external points are here, and then I put 2 vertices Z1 and Z2. Okay. Now, x1 could go to how many? Any of the 4 here or any of the 8 here. So, x1 has 8 possibilities. It can go to any of the 8, because see, Z1 and Z2 are dummy. If you look at the expression here, I think I wrote it somewhere for here. These Z1 and Z2 are dummy. You can there is no distinction between this factor and that factor. So, when you are contracting phi x1 with this, you can contract, or with that one you can contract. Okay, and as long as the identical contractions are done, you get the same expression. So, you get the same topology, same diagram if you join at any of, if you start with any of these 8 points. So, we have 8 possibilities to begin with, okay, that is what I want to say. So, let us say it goes to this one. Even if it goes to that one, you get still the same kind of diagram, the way I am going to construct. So, let us say it has chosen to go here out of these 8 possibilities. Then x2 has how many? x2 goes to the same vertex, or x2 is connected to the same vertex to which x1 is connected. So, x2 has to connect on z1, and there are only 3 possibilities. So, let us say it goes here. You can connect it this to here also, it's the same, it does not matter, these are identical. So, let us say we have connected here. So, you had 3 possibilities. So, let us count that. Now, x3 can go to how many places? x3 cannot go here, because the kind of diagram we are looking at, there x3 goes to the vertex to which x1 is not connected. So, x3 goes to z2, it does not go to z1. So, x3 should go to any of the 4. So, let us say it goes here. Then x4 should go to the same vertex to which x3 is connected, and there are 3 possibilities. So, you get 3. Now, this guy could go to any of these two, it cannot go here, because that will be a completely different diagram if you connect like this. Okay. It has go to here, so that you generate this topology. So, this one can go to any of these 2, let us say it goes here. So, you have 2, this guy has only one possibility. Okay. So, this is 1, 2, 3, 4. Okay, whatever that number is, this is the combinatoric factor. So, what you should do also is try to draw the same thing in a different way and convince yourself that they are all identical. So, you should be sure that this is really the combinatoric factor. So, for example, let me try to say this way. So, suppose you start here, but instead of connecting here, I said in the beginning you could connect to any of the 8. So, let us say connect here, and then this one has to go to the same vertex. So, it goes there. This one can connect like this, this one can connect like this, and then this here and that there. And this is looking bad, but it is the same diagram. Okay. Now, I want to write expression for this diagram. So, let us do that. So, I have this Feynman diagram. Okay. So, what is the expression? First, I should write down all the propagators. Okay. So, you have 1, 2, 3, 4, 5, 6 propagators. So, let us write. I have df x1 minus z1, this one. Then you have df of x2 minus z1. Then you have df of x3 minus z2. Then you have df of x4 minus z2, which is this one. Then you have df of z1 minus z2, this one. Then you have this propagator. again z1 minus z2. Okay, good. Then I recall that for each vertex I have to integrate over the internal points z1 and z2. Okay, for each vertex I have to do an integral, and each vertex comes with a factor of minus I lambda over 4 factorial. Let's go back and see here, minus I lambda over 4 factorial times an integration over the internal space time point. Okay, so let's write that down. So you have two factors of this, so you get minus I lambda over 4 factorial squared d4 z1 d4 z2. Okay, so this is the integral. Then I should write down, what should I write down? Yeah, I still have some factors to multiply, so I should write down first the combinatoric factor for this one, the number of ways in which I can draw this diagram, and that was 8 into 3 times this is 4 factorial. So let's write okay. Is something still missing? Well, yes, there is one thing missing, which is this is order lambda square diagram. So when you look at the prefactor, this, because you are expanding the exponential to order lambda square, it comes with a 1 over 2 factorial, right? I am talking about this factorial. So this is 1 over 2 factorial that I should multiply. And this is the expression for this this diagram that contributes to 4-point function. Okay, looks fine. Hopefully there is no mistake here. Okay, good. Let me give you some more examples. So I will give you an example of 4-point function. Okay, and basically the numerator, I am not looking at the full thing. Denominator I will worry later. Okay, so if I am looking at 4-point function, what are the possible diagrams? So I start with order lambda 0, then proceed like that. So this is one possibility. Okay, plus you have another possibility like this, plus you have another possibility like this. Okay, these all are added plus. So I think at order lambda to the 0, this is all. Now I go to the other terms, order lambda terms. At order lambda you can have the following. Okay, so there is a vertex here. Now I will not write x1 x2, it is understood this that I am writing always this way. Then there is another possibility at order lambda, which is this. Okay, so basically what I have done is I have taken this diagram and done what you call a order lambda correction here. Okay, so order lambda vertex has been connected here, and similarly here, and the same thing you can do for other ones. So you can have, okay, so these are all other diagrams which are order lambda, and then there are other kinds. So you can have this. So let us say you have taken this one, and the vertex you do not connect to any of these ones, but there are lines coming out of vertex that you connect among themselves. So you get one possibility like this. Okay, and then there is of course this possibility which you have seen. that you connect like this. So, vertex is here. So, this one is connected to this one here, this one here, this one there. Okay, so that is another possibility. Note that I am adding up all of them because that is what it is in the numerator. Then you can have I'm not drawing all diagrams, I am drawing some diagrams. So, now I am looking at order lambda square. So, this is order lambda, there is one vertex, this is order lambda 1 vertex, this is order lambda 1 vertex, but I can put a correction here. Okay, attach a vertex like this. So, this is order lambda square diagram. You see how you get this one, right? This one you get by doing the following. So, you have external point here, 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 then there is a vertex, then there is one more vertex. So, you connect like this. Okay, this is this diagram, and this is called external leg correction, and this kind of diagrams. And of course, you can put corrections here or on other legs also, not or and. Okay. Now, if you go to order lambda square, there are still more diagrams, many more, some of which are the following. Of course, you can do, if you go further order, further higher in order. So, this is 1 vertex, 2, 3, order lambda cube. This is order lambda cube diagram. Okay, and you can have this, I missed this, I should have drawn at order lambda square before I draw this. So, this is order lambda square. Okay, and there are many such possibilities. You can, maybe one more, I will draw the last one. You can also have this. Okay. Okay, maybe one more. Now that I am drawing, I can draw many more. So, from here I can connect like this. So, this is 1, 2, 3, 4. So, that is a 4-point vertex. 1, 2, 3, 4. So, that is another 4-point vertex. So, this is 1, 2, 3, 4, order lambda to the 4 diagram. Okay, so, this way you can draw all possible diagrams, and one has to be systematic, otherwise it is very easy to miss diagrams and get wrong results. So, care has to be taken in doing that. Okay, so, we will stop with these examples here, and we will continue discussion in the next video.